Hello there, wind energy students. Here's Dr. John Schroggy, and I'm talking to you today about the pages in your textbook that are about roughness as an influence on the local flow. Now, this is not exactly something new to us. We've actually already learned a lot about the idea of roughness when we were learning about the aerodynamic roughness length, which was our parameter z0. I mean, we saw it in a bunch of equations early in the course, things like, the log wind profile would be probably the best example. And let's make no mistake, the aerodynamic roughness length is going to come back. We're going to be seeing it again in other future lectures. So this is a good investment of our time to take a few minutes to reflect on the role of roughness on the local flow. Now, it's important to understand that roughness is not the same thing as orography. Remember, orography was, the contours of the terrain, like hills and cliffs and mesas and mountains and all that kind of good stuff. That can be very different than roughness, which is the actual character or texture of the underlying surface. A mountain that was, very rough, but maybe didn't have any vegetation on it. A mountain that was very rugged, as in the sense of like it, had a lot of terrain to it, but didn't have much vegetation or something like that, might have a very different roughness than you would expect. The roughness is a property of the surface itself, not like as in the contours and the shape of the surface. Roughness is not exactly the same thing either as obstacles to the flow, although we do tend to kind of get those two words a little bit tangled up. Now, we're going to be sorting out the differences between roughness and obstacles to the flow more in the obstacles lecture, which is coming up now. But just kind of as a nibble into the idea of the differences between roughness and obstacles to the flow, roughness is a property of the surface, as in like how the surface is interacting with the atmosphere, whereas an obstacle is an individual entity that's on the surface, like a building or a shelter belt of trees protecting a farm or something like that. Roughness is a property of the surface. But don't worry, we're going to spend more time on that difference when we get to obstacles. Now, when I looked through this section of chapter 5 in your textbook, what I was impressed with was exercise 5.8. Now, I think that really kind of illustrated the nature of the problem when talking about the roughness of a surface. Now, I didn't type the exact words of that problem out, word for word, but basically what it says there is that you are trying to do some kind of analysis of a field site, and you really don't know yet what the value of the aerodynamic roughness length, the Z0, is at your site. But you have some guess that you think it's somewhere between 3 centimeters and 10 centimeters. Now, if you are given the winds at some height, in the problem it tells you at some particular height, the wind, the problem asks you to figure out what the wind would be at the height of a wind turbine's hub. Now, let's take this problem apart because it's not entirely obvious how you're supposed to solve something like this. First off, what is this business of this range of estimates of the aerodynamic roughness length? They're saying, I don't know what the aerodynamic roughness length of this location is yet. We know that there's this rule of thumb for aerodynamic roughness length, namely that the aerodynamic roughness length should be about 1/30th of the average height of obstacles to the flow. You're going to see in a little bit I'm not loving this word obstacles to the flow anymore. But, okay, well that's saying, if I think that the aerodynamic roughness length could be as little as 0.03 meters, that means I'm thinking that maybe the average obstacle to my flow is 0.9 meters. If I'm thinking that it could be as much as 10 centimeters, 0.10 times 30 is 3 meters. So I'm saying I don't really know what I think the average height of an obstacle to my flow is, and that makes sense because there's a whole range of different sizes of obstacles in the area, and some of those obstacles are farther away, and some of those features of the surface are closer, and it's hard to know what, there's even bigger obstacles to the flow even farther away. I mean, if you want to go hundreds of miles away, there's buildings and skyscrapers, and if you want to go, say, closer, there aren't those things. I mean, it's hard to know exactly how to define the area around your site. And so this is actually a fairly reasonable range of possible uncertainty about what your aerodynamic roughness length would be. So the question is not so odd as far as like how you have this range. So what we're going to have to do is figure it out, the answer to this problem, using our low value of the aerodynamic roughness length, and then plug it in again using the high value of our aerodynamic roughness length. And from that, we'll get a range of estimates. We know our wind will be in this range, well, assuming we're right that our aerodynamic roughness length is somewhere in this range. Okay, just to be clear though, strictly speaking, this idea of the aerodynamic roughness length is formally defined only in the case in which we have a uniform surface, like it all has the same sorts of trees, or it all has the same sort of crops, or it has its water with the same heights of waves, or whatever, and it is of infinite extent. Okay, the flow has had plenty of time to adapt to it. There haven't been changes in the surface anywhere. Okay, obviously in any real life situation we have neither of those things. And so by necessity, this aerodynamic roughness length that we're working with is always an estimate, okay? It's an estimate that we can be getting from like empirical data. Remember that trick we did where we plotted winds at different heights on a semi-log piece of paper, and the intersection of the line that fit those points where it intersected the y-axis was another estimate of the aerodynamic roughness length? I mean, there's different ways of doing this, but they're always going to be an estimate, because the truth of the matter is it isn't really well defined for real surfaces anyway. Alright, let's turn to the second half as to how this problem is going to work then. It says you're given the wind at some height. I think the problem tells you 10 meters or something like that on an instrumented mast or something. And then it tells you, use that information now to figure out what the winds should be at the height of the top of some wind turbine. Okay. Now, your book has a suggestion. You can see up there in the top corner, I just sort of tagged this. This is how your book says to do it. It's clever, but we can be even more clever than that. What the book suggests doing here, and by all means go and look in the back of the book at how they solved exercise 5.8. But basically what the book says is take your equation that you got there for the log wind profile and use the winds that are given to you in the problem to solve for U star, because there's going to be a value of U star that matches to your low estimate of what the aerodynamic roughness length is, and from that you can come up, okay, now you have U star and you have Z naught, you can now come up with an estimate of the wind speed at 100 meters or whatever based on the log wind equation, and then just do that same procedure again, but now for the high estimate of the possible value of the aerodynamic roughness length. And this is really clever. This is a way of doing it where they have figured out this tricky business. Remember U star, it's the friction velocity. It's a very hard thing we're going to have to think more about it later in the course, but it's a very hard thing to understand. It's about the flux of momentum in the vertical flux of momentum in the atmosphere. Hard thing to understand. And hey, we can use the information we're given in the problem to solve for it. And I guess, you know, that's modestly clever, but you can actually do better than that, because remember that derivation that we did in the class. You don't actually need the U star at all to make this problem work. What you can do is take the wind that you're given and the value of zeta naught, your Z naught rather, that is your low estimate, plug them in and get a wind estimate at your height of your wind turbine's hub, M2. M here being our symbol for wind speed in this particular form of the equation. And then do the same procedure again, but plug in your other value of Z naught, your high estimate of the aerodynamic roughness length, and then you get a different value of M2, the wind speed at the height of the hub, and you don't even have to mess with that whole business of the U star. So, I mean, this is even more clever than the clever way that your book was doing it. But either way you do it, you come up with the same answer. You end up with wind speed estimates associated with your high and low estimate of the aerodynamic roughness length at the turbine's height of 8.8 meters per second and 9.3 meters per second, based on the two different values of the aerodynamic roughness length, which, you know, hey, that's a fairly narrow range of wind speeds. It sounds like, well, I guess we didn't really need to be so worried about our roughness length value that we were trying to come up with, except, well, actually, that's not so small of a range of wind speeds. I mean, that works out to a 6% range. I'm not that thrilled with that range. More importantly, it isn't exactly the wind speed that is what you're worried about at the height of a turbine. It's actually the flux, the transport of kinetic energy, because that's what determines the rate at which you're converting wind power into electricity. And that, remember, is proportional to the cube of the wind speed. Well, in this particular case, if you work out the difference in the amount of energy you can capture from wind speed at 9.3 meters per second and 8.8 meters per second is a whopping 18%. Well, that's way outside the ranges of like what we can be tolerant of in terms of our errors of how much energy we're going to be producing. Clearly, the investors on your wind turbine are going to want better estimates than that as to how much power we're going to be getting and so on. What I want to draw your attention to then is what a pain in the butt this roughness length stuff is. I mean, we had perfectly reasonable amounts of uncertainty associated with our estimates of Z0, and it turned out to be resulting in completely unacceptable uncertainty in our forecast of the power we would be able to produce. That means that we're going to have to get better at coming up with estimates of roughness. And that's a whole thing. Okay, that's a whole business of surface modeling and different techniques of, like, you know, the technique of using the instrumented masts to come up with estimates of the roughness length like you did in the previous module and so on. All of which is just so much work. Roughness is such a complicated problem in atmospheric sciences, and it gets so much worse because roughness changes. It's not a constant even at a given site, much less from site to site, but even at a given site, the roughness changes, in particular with respect to the seasons. Now, to understand that, take a look at the picture we've been using in the background of this diagram here. On this PowerPoint deck here, I chose a lovely picture of some maturing corn in the background there. Corn as a crop has some roughness length associated with it. As the flow flows over this corn, there is a certain amount of frictional drag that is being exerted on the flow by the corn, etc. And corn starts out as little bitty plants. Over the course of a couple weeks, it gets to be 8 feet tall, and then at the end of the season, the combine comes through and harvests the corn and leaves behind dead stalks. Well, clearly there is a radical change in the roughness of the surface over the course of a year, going from relatively smooth ground that has been prepared for planting to, which that's another story, to corn plants that will be rapidly changing their height to cut down and bare ground. The roughness length will be changing over literally orders of magnitude over the course of the year at this one given site in a rural location, which would be a lovely place for a wind farm. So this becomes very complicated to actually be able to there's a whole subdiscipline of atmospheric sciences and environmental sciences that's about surface modeling and so on. Being able to derive the cycle of the annual cycle of the properties of land and so on. And this is an example of the kinds of output that somebody in these kinds of disciplines would be doing, where for example, this is actually a map of the surface properties that are known by a particular weather forecasting model called the WRF model, the Weather Research and Forecasting Model. And it actually maintains a huge database of the surface characteristics at every little, at some very high resolution over the whole world. And so they were just zooming in on different domains and showed, how you can see how all of these individual grid elements within the model have been characterized as, different kinds of urban, industrial, wooded wetland, deciduous broadleaf forest, mixed forest, etc. And each of those pixels, there is some associated annual cycle to the estimates that will result in how the model will decide what to use for the value of Z0 at that location. Some of them even get more sophisticated about it and take into account things like growing conditions and so on. Clearly the roughness will be different depending on how the plants are doing and so on. Oh my gosh, it can become basically infinitely complicated to be thinking about the roughness associated with the surface. Good thing we've got the oceans, where the oceans are just water, right? Surely we can just look at the water and say, this is going to be pretty straightforward, we'll have a very low roughness value. The answer is no. Even over open water, this idea of the roughness of the surface can become incredibly challenging. I mean, like, I picked a picture here that I found online someplace of a very smooth ocean, where clearly flow over this is not experiencing all that great of an aerodynamic roughness length, but obviously that can vary over many orders of magnitude. I mean, clearly we have a much more rough ocean surface here in this inset picture. The book actually provides you an equation that gives you the values of Z0 over a fairly wide range of wind speeds. It's a fairly standard parameterization. I didn't put it in here just because it's kind of a pain to type up an equation you can just see in the book anyway. And so based on different wind speeds, you can come up with different values of Z0. Now, to some extent, that's kind of that kind of begs the question, right? I mean, if you already know the winds, why would you need to know the value of Z0? And if you don't know the value of Z0, where'd you get the winds? Unless, of course, well, anyway, get it? It's kind of a problem. But I can see from like a modeling and theory point of view, it makes some measure of sense. And the equation they give you, they somewhat glibly mention to you, oh, this works for anything greater than, any wind speed greater than 3 meters per second, or about 6 miles per hour. Okay, great. It's some nifty little equation. Well, why does it not work at low wind speeds? Because low wind speeds are a real problem in meteorology. Low wind speeds and how they interact with oceans are very, very complex, because you get these very strange little ripples on the surface. When the ocean is relatively flat, or a lake is relatively smooth, if you look closely, there's actually some fairly fast-moving little ripples on the surface. Those are a type of waves called capillary waves, and man, atmospheric scientists hate capillary waves. Capillary waves are just these little ripples that just look small and harmless, but they are actually, if you actually examine them very closely, their edges are quite steep, which means they actually have a surprisingly large aerodynamic roughness length. You would think those little ripples are just not really interacting with the wind at all, but in fact, for their size, they're a huge impact on the wind. And they make for a surprising amount of friction between the wind flowing over the ocean. Admittedly, it's going to be a weak wind, like, you know, less than 3 meters per second, or less than about 6 miles per hour. But they're having a huge impact. These little ripples are having a huge impact on the wind, and they produce a lot of friction. They actually are, I can't even tell you how big of a complicated problem they are in regard to, like, forecasting the roughness. The roughness of the surface of the ocean has a lot to do with, like, the flux of sensible heat, that is to say, like, conduction of heat out of the ocean into the atmosphere, or the flux of latent heat, that is the rate at which water vapor evaporates off the ocean into the atmosphere. All that capillary waves totally mess with. This is actually a major source of problems in models right now. But it's also a problem that smart researchers are working on, and we will have good ways to understand how low wind speeds interact with the ocean some fine day. Man, roughness is a complicated question, and it's got lots of messy details to it, and I wish I could give you better answers as to how to solve it, but it's so much of an issue of just work. It's just work of gathering observations, gathering wind profiles, coming up with estimates, trying those estimates under different seasons, different times of year, under different growing conditions, before you can just come up with good estimates of roughness for any given location. It's a good example of where there just isn't a shortcut, where there's just a number you can look up in the book or something like that. All right, before we get done with this lecture, let's do a couple quick questions. Question 1. Could a surface have complex orography, you know, like mountains and stuff like that, but have a small value of the aerodynamic roughness length? Yes or no? Make a choice from those two options based on what you now understand about roughness, and we'll get some feedback before we move on to question 2.